In the design of timber structures, Eurocode 5, which is a European standard for the design of timber structures, introduces several factors which adjust the design value of a strength property of wood. One of the most crucial among these is the modification factor kmod. Since timber is a time-dependent material, its strength is influenced by how long a load is applied and the environmental conditions it is exposed to. The modification factor accounts for the effect of load duration and moisture content on timber's structural properties, helping engineers design structures that remain reliable and durable over time. In this video, we'll break down what the modification factor is, how to apply it in real design scenarios, and why it plays a critical role in safe and efficient timber construction. The modification factor is a crucial numerical value in timber construction that adjusts the usable design strength of wood and wood-based materials to account for various factors affecting their performance. It is determined by two key factors, the load duration class and the surface class. We covered these in our last two videos, so it's helpful to review those first. But here is a quick recap. As we discussed in our previous video on load duration classes, Eurocode 5 categorizes loads into 5 distinct classes: permanent, long-term, medium-term, short-term, and instantaneous. Each class represents a different duration of load application, ranging from more than 10 years for permanent loads to just moments for instantaneous loads. In another video, we explored the 3 service classes defined by Eurocode 5. These classes, 1, 2, and 3, represent different environmental conditions and their impact on timber's moisture content. Service class 1 represents dry, indoor conditions, while service class 3 represents fully exposed outdoor conditions. Depending on the load duration class and service class, the modification factor will give you one of these values for solid timber, glue laminated timber, laminated veneer lumber, and plywood. In structural engineering, particularly in timber design, the design value of a strength property of a material is calculated by adjusting its characteristic value of a strength property to account for real-life conditions and safety. This is done by using two key factors: the modification factor and the partial factor for a material. We've already discussed the modification factor and how it affects a material's design strength. In addition, the partial factor serves as a safety net, accounting for uncertainties and adding a buffer to ensure structural reliability. Together, these two factors are essential for determining a realistic and safe design value of a strength property of a material. This design value is given by the following formula, where XD stands for the design value of a strength property, kmod stands for the modification factor, XK stands for the characteristic value of a strength property, and gamma M stands for the partial factor for a material. The X can be replaced with different strength properties such as compression or tension. Let's walk through an example using CLT under a medium-term load in a service class 1 environment. This load duration class and service class give us a modification factor of 0.80. with a characteristic compressive strength of 21 newtons per square millimeter and a partial factor for a material of 1.25, the resulting design strength would be 13.44 newtons per square millimeter. The modification factor is crucial because it decreases or sometimes even increases the design strength of timber to realistically represent how timber behaves under different conditions. For example, timber that's loaded for a short time can safely carry higher loads than timber that's under constant long-term loads. Similarly, timber that's kept dry performs better than timber that's exposed to high moisture levels. By incorporating the modification factor in the design of a building, engineers can accurately account for the time-dependent and moisture-sensitive nature of timber, ensuring safe structures. This adjustment helps prevent overestimating timber capacity, which could compromise safety, while also avoiding unnecessary structural conservatism, which leads to inefficient use of materials. For example, if a modification factor is not applied to account for long-term loading, a floor beam might be designed assuming it can carry the same load continuously as it could for a short duration. Over time, however, the sustained load could cause the timber to creep and deflect excessively, or even fail structurally, potentially endangering occupants and requiring costly repairs or reinforcement. This clearly illustrates why modification factors are not just theoretical adjustments. They are essential for real-world safety and performance. A thorough understanding of the modification factor is essential for successful timber design. It allows engineers to tailor their designs to the specific loading scenarios and environmental exposures a structure will face, promoting durability and efficiency. Mastering the modification factor and its relationship to load duration and service classes empowers engineers to optimize timber designs confidently and sustainably. Thank you for watching this video. If you'd like to learn more about the load duration classes and service classes, take a look at one of the videos that are on your screen right now. And if you want to learn more about the world of mass timber as a whole, subscribe to this channel.